So this part of the section of lectures on spectroscopy, we're going to focus on sources of radiation. So in particular, we're going to look at optical sources and lasers, and I'll also mention a little bit about techniques that you can use to produce X-rays as being the most common sources of radiation that we use in spectroscopic experiments in day-to-day lab work. Okay, so just to reiterate again, in our generic spectroscopy experiment, we have several stages. We have a stimulus, a radiation source, which is what we're focusing on here. You might expect to have some kind of optics to collimate or monochromate or filter and focus the light or the radiation. You obviously have your sample. You have some signal processing optics, which are for doing things like dispersing by wavelength or frequency, and possibly filtering and reflection, angle measurements, so just seeing what's going on. And then the final part of it is to go and have the detector. So we're going to be talking mainly about, at this point, about the radiation sources. So possible stimuluses, of course, span pretty much the whole of the electromagnetic radiation, and you might want to be thinking about these in terms of a wavelength. Wavelength is most important when you're wanting to think about scattering of objects. So at the kind of long wavelength end of things, what you're interested in then is the scattering of macroscopic objects, and you kind of typical example of something where that might be relevant is if you're thinking about a radar, where you're scattering off centimeter wave or longer radio waves in order to go and detect where an object actually is. For most sort of say solid state physics type experiments of one sort or another, you're probably more interested in things like crystal lattice spacing or molecular spacing, in which case your wavelengths you're interested in is going to be down at the nanometer to angstrom range, because of course the scattering of radiation is essentially diffraction, and as you know, for diffraction the wavelength needs to be of a similar size to the objects you're interested in scattering off, and so that's really what's controlling which wavelength you want to pick. Alternatively, if you're thinking about your stimulus in terms of energy levels and energy involved in the radiation, then this is where you're maybe looking for energy transitions and resonant processes going on. So again, different parts of the electromagnetic spectrum would be useful in different contexts. So you might be looking, for example, at things like molecular bending and stretching modes, in which case you're looking at energy levels that are at the low end. So for example, often in the infrared zone, would you start seeing molecular deformation modes coming in. You going a bit further up in energy, you're starting to look at things like typical band gaps in materials. So for example, the band gap in silicon is about an electron volt, which is getting close into the visible, well, it's around about the visible light range. Coming up in energy a bit further, you start looking at things like energy transitions in atoms. So those are often in the kilo electron volt sort of range. And then as you go further up, you start getting into the sort of gamma ray type range. Then you're obviously into nuclear binding energies. So again, depending what sort of energy transition you're in, will help determine what type of stimulus wavelength you want to use. And then finally, you might be thinking more about things like frequencies of the radiation involved, and this obviously is where you're thinking about the timescales. And again, different frequency ranges will be useful for different types of experiment. In this region where we kind of tend not to go as high up in frequency as you go up in along the electromagnetic wavelength spectrum in energies or wavelengths. But if you're looking at kind of gigahertz ranges, then the timescale for electron spins to precess and to oscillate is around that region. And so you get magnetic resonance techniques, ferromagnetic resonance techniques. If you're in nuclear magnetic resonance, you're at a bit lower frequencies. And some of the nuclear magnetic resonance relaxation techniques, you're in the megahertz or lower range. And then as you go up further into terahertz, then you start getting into the point of looking at the actual frequencies at which molecules are vibrating. And that becomes very interesting for, say, fingerprinting molecules. And so over the last 20 years or so, there's been an awful lot of interest in terahertz radiation for fingerprinting different molecules, largely driven, unfortunately, by the need to go and do things like airport security and to fingerprint plastic explosives, which are otherwise very, very hard to go and detect. So really the take-home message here is that you can pretty much use anywhere on the electromagnetic spectrum. But what we're going to mainly focus on at the moment now is the production of light in the around about the optical range, and then do a little bit about talking about X-ray production as well. Okay, so the important thing in all of these aspects is to think how electromagnetic radiation couples to energy transitions in a system. So in order to go and produce our radiation, to produce our light, we're going to want some kind of energy transition that's going to be very well defined if we want a single wavelength of light coming out. And that energy transition has to somehow interact with light. And we have similar questions actually when it comes to what's actually going on inside the experiment and also what's going on inside our detector. In all of these cases, essentially, we somehow have to couple an energy transition to electromagnetic radiation. And for that to be the case, your energy transition has to have some kind of transition dipole, meaning that going from one state to the other state somehow is going to generate a dipole, because that dipole is what's going to interact with the electric field, the oscillating electric field of electromagnetic radiation. So if we think here about going from an s orbital to a p orbital, you might say, okay, well, is there actually a polar transition here? It's not immediately obvious if you just look at the time-independent solutions of the Schrodinger equation, that this should naturally lead to a changing dipole. But in fact, if you work through it, then the time-dependent superposition of these two states, which is what's going to happen as you go through an energy transition, you're going to be, say, in the s orbital state, which might be the lower energy ground state, and you're going to transfer to the p orbital, which means in the process of doing that, you go through some linear superposition of the s and the p orbitals, and then you end up in a state where you're entirely in the p orbital. So it turns out, if you actually do the maths, that transition going from the s to the p orbital does in fact have a dipole, and that dipole can therefore interact with an electric field if it's going at the right frequency to match the transition frequency and the transition energy. Okay, so that means, yes, in principle, this is going to be an optically active energy transition. What you need to then think about is how's this going to work. So generally speaking, we might want to think about three types of transition which would involve light in the energy transition. So first of all, you could expect there to be maybe some kind of optical absorption process. So in other words, you're in the ground state, you absorb some energy in the form of a photon, and that puts you into the higher energy state. So in order to go and do that, as well as having the transition dipole, obviously your energy translation has to involve a change in energy of the right size, and it has to involve not a significant change in momentum, so that you're able to conserve both energy and momentum in that process. Okay, so we have an absorption process. You might then think about the opposite state, that you're in the higher energy state and you spontaneously go down to the lower energy state and emit a photon in the process. So you might have a spontaneous emission process. And then the final one you might want to think about is a stimulated emission process. And in this case, you're in the high energy state, but actually it's the presence of a photon of the right energy that interacts with the potential to have a transition dipole and sort of kickstarts that transition dipole from actually working. So in other words, it actually triggers the transition. And this is very important, as we'll see, because what it means is that the photon produced by that transition is going to be related to the photon that triggered it in terms of the phase and the energy. So this stimulated emission becomes the sort of transition that gets kind of interesting. So, and one can go and sort of calculate what the various transition probabilities should look like. So let's go and look therefore at how we might actually apply this. And so this obviously is light amplification by stimulated emission of radiation, aka a laser. So the important things in a laser is that you have a multi-level energy state. So kind of minimum you have 3 energy states. And what you're looking for is you're looking for a state where you can have a rapid non-optical spontaneous relaxation into a state where you have a relatively low probability of a spontaneous optical emission transition, but it does have a good probability of a stimulated emission transition. So the stages we go through for actually operating the laser, the first thing we do is we start in the ground state. So in this diagram here, we have, maybe this is a gas laser, and we have a series of atoms, and we're in the ground state, and we use an electrical discharge in this case. It doesn't have to be an electrical discharge, but in this case, we use an electrical discharge to pump all the atoms into an excited state. So we've now achieved what is described as a population inversion, meaning that you'd expect, given the temperature you're in, the equilibrium state would be to have everything in have all the atoms in their ground state. But because we've taken it out of equilibrium, we've put it into this non-equilibrium state where you've got all the atoms in the excited state. So we've had a population inversion. Now, in our kind of archetypal system here, those atoms will rapidly relax, but they don't relax all the way to the ground state. What we're looking for is a state where they can relax into a metastable energy level just below here. And the important characteristic of this E2 state that we're now in is that those atoms have a relatively low probability that they're going to spontaneously decay to the ground state. So they're going to just hang around and sit there for some reasonable finite time. And the other requirement of that state is that it's an optical, is that the transitions are optically active. So in other words, when an atom does drop to the ground state, it's going to emit a photon. And the final thing we're looking for is that that transition doesn't happen too frequently spontaneously. So we need to have at least it can't be a 0 probability of a spontaneous emission, but it needs to be a small probability of a spontaneous emission compared to the probability of a stimulated emission. So what happens is that at some time, 1 or 2 of those atoms will spontaneously decay, and they emit photons. And the photons they emit are of the energy that corresponds to the energy transition. So those photons then start traveling through the cavity, and then because the stimulated emission probability is much higher, it's very likely that that one photon is going to interact with another atom that's in the higher energy state, in the E2 state, and cause it to also drop down in energy. Now, because the photon the stimulated photon is at the same phase, and it's obviously the same energy as the original photon that did the stimulating, those 2 photons are now same frequency, same wavelength, and in phase with each other. So that process sort of continues, and those photons rattle along our gas. And then the key thing we go and do is we have to make a cavity. So at either end of our gas tube, we have a set of mirrors. So at one end, you would have basically as near a perfect mirror as you can get. So what's called a high Q mirror. So something that absolutely stops the light from going through and sends it all back again. And that may well not simply be a a polished and coated bit of glass. It could, for example, be using a material we've got total internal reflection at a refractive index interface, or you can make use also of Bragg reflection to make very, very high quality mirrors. And at the other end of our cavity, we want something which is a partial mirror, meaning that it reflects nearly all of the light, but not quite all of the light back down. So that could be a perfect mirror with a hole in it, or it could be something which is just partially reflective and is, say, 99.999% reflective rather than 100% reflective. And so what happens is most of that light that we've triggered rattles backwards and forwards up and down the cavity. And every time it goes up and down the cavity, it stimulates yet more energetic atoms to collapse down to the ground state and emit even more photons. And all the photons you're producing are the same wavelength, same energy, and in phase with each other. Now, of course, you can't carry on doing that forever because eventually you run out of atoms in the higher energy state. So you have to continually repump the population. And so you end up with a kind of dynamic process where you're pumping the energy distribution up, and then you're, through stimulated emission, you're having them relax back down to the ground state. And if you want to make a continuous wave, then you have to keep on doing that continuously all the time. So all the time you have to reach some kind of dynamic equilibrium where you're putting energy into the system to pump the atoms to the higher energy state. They then relax to that second energy level, and then they decay to the ground state, emitting photons, and you keep that process driving round and around and around. Often in many of the lasers we look at, in fact, that's not a particularly feasible process. The process of charging has to be kind of a one-shot process. So in that case, what you do is you end up making a pulsed laser source. And in fact, some of our fastest, most accurately timed systems are pulsed laser sources. So in that case, what you do is you pump the system up with, say, an electrical discharge pulse, or possibly even you can in some cases use an optical pulse. So you could have a light source that's pumping your laser with flashes of light that have enough energy to transfer you from the ground state up to the E1 state. And that light source doesn't need to be a laser, doesn't need to be phase coherent. It could just be anything which produces photons of enough energy. It doesn't even need to be monochromatic. As long as it doesn't have too many energy states, you can populate with it. And then the whole decay process will undo the population inversion within a very, very well-defined period of time, because it's going to be dominated just simply by how much lasing material, how much gas or whatever it is in your system that you've got there that can go and decay. And so you produce a pulse of a very, very consistent duration, and it's also a very, very short duration. So you can produce femtosecond laser pulses using this sort of technique. So as I said, most of the light is rattling backwards and forwards in our cavity, but because the right-hand mirror there has a hole in it, or it's only partially reflective, some of that light is escaping. But the light that's escaping is all extremely phase coherent, and of course its energy scale is dominated by the energy levels inside the system. Now, actually, it turns out that it's not completely perfectly monochromatic, because it'll depend a bit on the type of laser you're using. But for example, if this is a gas laser, so we have a gas cavity in here, then those gas atoms are moving around all the time. And so there are small amounts of red and blue shifting going on. So your laser is not perfectly monochromatic, but it's not far from being perfectly monochromatic. If it's a solid state system, then again, it depends on how exactly reproducible you've made your energy levels in your solid state system. So the details of how a laser is made and how it operates can tell exactly how perfectly monochromatic is. And likewise, if you have more spontaneous emission of light, then it's going to be less phase coherent. So although lasers are very phase coherent and very monochromatic, they're not perfectly monochromatic and they're not perfectly phase coherent. And that can get an issue in some types of experiments. And so the process sort of goes on, and we end up producing our laser light. And so effectively what's going on here, of course, is we've amplified what started off as 1 or 2 photons as being amplified into a much more intense light source, which is why we like using lasers in labs, because it's an extremely well controlled and very, very brilliant light source. Okay, so in practical terms, how do you make them? Well, there's a whole range of different ways of going and doing it. In practice, most of the lasers you use in a lab are most likely these days to be a solid state laser. So they're a diode laser made out of a PN semiconductor junctions with some kind of quantum well structure inside them to go and define those energy levels. And you electrically pump them, and you create the electron hole pairs, and then they recombine. And these things are cheap. They're pence to pick up. They're fairly ubiquitous these days because, of course, any kind of optical disc reader, so a CD, a DVD, a Blu-ray, all have solid state diodes in them. Laser pointers, they're all over the shop. The other type of laser you might use in a real lab environment are often gas-based. So the kind of classic one is a helium neon gas laser, which uses a mix of helium neon and produces a red light. And in fact, actually, the solid state PN lasers that are used, the red laser pointers and so on, are basically designed to try and replicate what a helium neon laser is using, and they're producing light of about 630 nanometers. But there are other options, things like the near-dim YAG lasers, which those are examples of systems where you have your actual lasing population as individual atoms. They're embedded in the matrix, and you can't connect to them electrically, so these are optically pumped systems. And then there are more esoteric and sophisticated systems. So polariton lasers are kind of a cool new thing. In this, you're actually creating electron hole pairs. But then if you think about an electron hole pair, although the electron and the hole are both spin half particles, the pair together is a spin integer particle. And in those cases, then you can create a whole population of electron holes, which can form a Bose-Einstein condensate. And then the kind of cool thing is that if it's a Bose-Einstein condensate, they're all in the same state. So if you can get one electron hole pair to recombine, you get all of them to recombine together if you engineer it right. And so that produces your phase coherent pulse. So that's an example, in fact, where although we started off by talking about it being stimulated emission, in fact, there is no stimulated emission in a polariton laser. It's because the Bose-Einstein condensate is collapsing all in one go, because it's only a single quantum state. And it's kind of pretty cool that people actually managed to get that to work as a concept. But as I say, the primary sources of lasers you actually use in the lab are either the solid state diodes, or their gas lasers, helium neon, argon, and particularly another one we actually have in Leeds is we have a krypton fluorine gas laser, an excimer laser, which produces light in the UV, and we use this for laser ablating things. So we actually fire our laser into a target of a known material, and that creates a splay of that material, which we then use as a thin film deposition technique. That, however, is another lecture for another day. So this just gives you kind of an idea of the range. I was saying about some of the different types of lasers. But you can see we've basically got everything covered from near infrared through to near UV. In telecommunications, actually telecommunications tend to work at about a 1 micron range. So they're using some of these near infrared lasers. So these sort of 1060 nanometer wavelength are the ones that are used for telecommunications. So essentially transferring data around the internet. And then as you sort of work away into the visible light, you've got the, things like obviously the ruby lasers, and then we're into helium neon laser, gas laser there, you see at 633 nanometer, and there are a lot of diode lasers which operate, semiconductor lasers, which operate in a similar range to that. And you can carry on through a variety of different sources. We seem to have got helium neon in twice there. At 633 nanometers, but coming on down, the argon lasers I mentioned in the sort of green light lasers and going into blue. And if we carry on down, so then we've got the, again, lots of gas ion lasers involved there. And then coming down right near the bottom, you've got the xenon chlorine, and actually my krypton fluorine laser is a bit further into the ultraviolet still than that is. So pretty much pick your wavelength, and you can pick your laser to go and give you what that light that you want is. What you don't have is completely free choice of wavelength. There are limits to all of these technologies. The reason semiconductor lasers are quite popular is they're a lot easier to tune to a particular type of wavelength. So by changing things like the size of a quantum well, you can change the spacing of energy levels, and that becomes something that one can actually control in the design of the laser. Whereas the gas lasers, you're much more constrained to the energy transitions that are available. However, in some cases, you don't want a white light source. You don't want a single monochromatic light source. What you want is a white light source, so a broad spectrum light source. So in this case, what we're looking for, and the ideal thing would be something which produce equal intensity across all different frequencies, but that tends not to be the case. So if you're wanting to make a broad light source, then your kind of starting point would be to say, for example, try and make a very hot black body and use black body radiation as your light source to give you the broad spectrum. So that is basically what tungsten halogen lamps are doing. It's just get that tungsten filament as hot as possible, because tungsten has the highest possible melting point of all elements, and therefore make a very, very high temperature black body source and use that. The other possibility you can do is to use an arc lamp. So what you're doing there is you're trying to create a plasma in something like a xenon gas. So a plasma is where you've stripped the electrons away from the ions, and so you have a separate gases of the positively charged ions and the negatively charged electrons, and they have effective temperatures of thousands of Kelvin. So in terms of our black body radiation, they're a really good white light source. They're a very, very high effective temperature. They also have, within that, they have particular atomic energy transitions going on. So you also get some bright light, particularly bright spectral lines in there. So you've got a combination of the black body and the energy transitions going on top of it. Xenon arc lamps are particularly good at giving you high intensity visible and UV emission light. And then there are actually some tricks you can play with lasers in order to make them white light sources. So one particular thing you can go and do is you can engineer a fiber optic structure so that it has a particularly well characterized dispersion relationship. So by engineering your fiber optic, so I mean, I remember actually seeing an example of this being done at the University of Bath, where they'd made a fiber optic out of a series of glass cylinders. So it wasn't just a simple glass rod, it was a two-dimensional lattice photonic crystal. And they designed that so it had a particular dispersion relationship for light, so that although you put monochromatic light in at one end, what came out had been spread out in wavelength and frequency, and so it made a white light source as well. So as long as you're prepared to go and have a few hundred meters of this extremely fragile and expensive fiber optic cable in your white light source, you've got a laser-based white light source. But again, for lab equipment, typically what we're using is either tungsten halogen lamps or xenon arc lamps as the most likely source You can also get mercury-based lamps as well, although they're a little bit scary because if you have mercury vapor and your light bulb breaks, then you have a slight health and safety problem. Okay, so that's all about optical sources. What about X-ray emission? So we like using X-rays because they have a very good wavelength for looking at structure of solids, and also because the energy scale is good for electron transitions, which can tell you information about chemistry and as well as elemental fingerprinting. So in a lab, typically what you might be using is some form of X-ray tube. So essentially what you're doing here is you're accelerating electrons. They're typically made by thermal emission. So you have a cathode which has a filament made out of tungsten. You heat it up, it gets very, very hot. Those electrons are released. And then you accelerate them across a large potential difference into an anode made of some kind of metal. And then the incoming electrons cause they knock electrons in the copper out of their core energy levels, push them up to very excited energy states, and then it's that energy transition coming down from the excited energy state back into the core state that emits the characteristic X-ray photons. So if you actually look at the spectrum coming out of an X-ray tube like this, then what you see is you see these characteristic X-ray lines, but you also see this big background hump, which is called Bremsstrahlung radiation, and Bremsstrahlung basically means braking or decelerating. And that tells you what's going on here. So we're firing these high energy electrons into the copper, and then they're undergoing a massive deceleration as they go into the copper. And if you accelerate a charged particle or decelerate a charged particle, it emits radiation. And so this is what you're seeing. You're seeing the radiation being emitted because you're decelerating a charged particle. And so you get this sort of characteristic lump. And that's kind of the weakness of these X-ray sources, is that you then have to go and filter out all of the X-rays you don't want and leave just the ones you are interested in. So typically what we're looking at is what's called the K-alpha transitions. And even then it's a bit more complicated because if you look at the energy transitions in copper, if you look at the energy levels, then because the p orbitals have slightly different energy levels inside the atoms, even these K-alpha lines are then split into different pairs of wavelets. You tend to get a splitting in the result. And so if you actually really want a monochromatic X-ray, you then have to go and do even more filtering as well. And in a lab source, typically what we do is we bounce it off a diffracting grating. Typically we use something called a 4-bounce filter, which means the X-rays actually bounce off four gratings, and only X-rays of the correct wavelength manage to make it through that monochromator without being absorbed by the surrounding material. But if you choose your right target material, you can get a range of different X-ray energies. As I say, so the copper is the most commonly used one, and mainly using the K-alpha radiations, which are about 1.5, just over 1.5 angstrom wavelengths. But you can also use nickel and iron and manganese. The reason you might want to use different ones is there's not much point trying to do an experiment where you're looking at copper if you're actually using if you've got too much of a danger that your X-ray is going to be absorbed by the material that you're trying to study. So you'll pick different X-ray tubes sometimes to suit a particular experiment, but generally speaking, we're using the copper K-alpha. Okay, so that's all very well, but X-ray tubes have a limited brightness. I should say you can play quite a lot of tricks with X-ray tubes. So the problem is the anode gets very, very hot because you're depositing a large current of electrons at a high voltage in it. So cooling your anode becomes very, very important. And you can do things like you can make an anode that's actually a big disk that spins around and around very fast, so that any one part of it only sees the electrons bombarding it for a very short period of time. And so you can run with a higher current, you can produce more electrons like that, and produce more X-rays, or the very latest ones actually have liquid sources, and you're literally pouring the anode past the electron beam in a kind of continuous loop, and so it doesn't matter that the anode is getting very hot, because you'll just keep the flow up fast enough, and you can manage to keep the whole system running cold enough that it doesn't melt your instrument. But if you want to go brighter than that, then we need to go to a synchrotron. So this is in fact a model of the Swiss light source, because it happens to be the synchrotron I was at most recently. And what happens in the synchrotron, again, it's using the idea that a charged particle which accelerates is going to emit radiation. So in this particular case, what you do is you take electrons and you accelerate them up to relativistic speeds. So we have first of all, a linear acceleration, a LINAC, which gets started. You then feed it typically into some kind of a booster ring, which is accelerating electrons round and round and round that loop faster and faster and faster. And you basically build a pulse. So the electron gun fires a pulse of electrons, accelerated down the LINAC. You then send it around the booster ring, gradually speeding it up and speeding it up and speeding it up and speeding it up. And then after enough cycles around the booster ring, you direct it into the main storage ring. And then what happens is that pulse of electrons travels around that storage ring, going round. Now, we say it's a ring, but actually it's not really a ring. What it actually is a section of straight lines, and then corners, and a straight line, and then a corner. And the reason for that is that as the electrons go around the corner, they go around the corner with a magnet. So basically have what's called a bending magnet that causes the electrons to, through Lorentz force, to go around the corner. But changing direction is a change in velocity, is an acceleration. And so as the electrons go around the corner, they emit X-rays out along the tangent to the ring. So in our picture there, that's what those lines running out are. Those beam lines are picking up X-rays that are being accelerated around the corner. But actually a more effective way, it turns out, of getting the electrons to produce X-rays for us is, in fact, inside the straight section. We don't just have them fly straight, we insert an array of magnets and have the electrons wobble up and down, or move backwards and forwards. And because we can control the periodicity of that grating of that array of magnets, we can control, and we're also controlling how fast the electrons are going. We're able to control how fast they oscillate, and therefore what the wavelength of the light is. And you can also get a much more intense light source from an insertion device than you do from the bending magnet. So in a modern synchrotron, what you have is beam lines on every corner, and then also in the middle of all the straight sections. And so typically a synchrotron might have as many as 36 or more separate beam lines, each of which are doing their own type of experiment. And then what happens is those X-rays, those electrons fly round and around the ring, and every time they go past you, they emit a pulse of X-rays. And obviously, gradually over time, that pulse loses definition, it gets a bit dispersed. It also, you lose some electrons because they just randomly collide with residual gas molecules, even though this is all done in a vacuum, and your light pulse decays over time. So then every 10 minutes or so, the electron gun fires again, and you get another burst of electrons into the booster ring, and then injected into your synchrotron, and you see your light levels go up again. And every single pulse of light that's going past you is coming past at many millions of times a second. So typically the Swiss light source, if I remember correctly, runs at 80 megahertz. So you get a pulse of X-rays every 80 megahertz. And then that allows you to go and do some time resolved measurements as well. So you can get some really quite sophisticated things going on where you're not just using different wavelengths, but you're also able to do different timing experiments. And so some of the pump probe experiments I was talking about in some of the earlier lectures, you can do with X-rays at a synchrotron. So in that case, you're pumping your system, say electrically, with a a pulse that's timed to the synchrotron clock, and you're probing it with the X-ray pulse, the X-ray flash that comes from the synchrotron. Okay, so this is in practice what a bending magnet looks like. So at PSI, they have a little section of the beamline that's sitting out as part of a visitor center exhibit. In fact, just outside the beamline we use. So where that door is, that's the control cabin of the hutch we use. And then the blue is the bending magnet, and you can just see the pipes, the ultra high vacuum pipes coming out at a slight angle. And then the red is a quadrupole magnet, which is used, it's not actually an insertion device, it's being used to focus and reshape and collect the beam of electrons back up together again before you go into the next UHV section. And then if you walk down towards the synchrotron ring, before you go through things like a monochromator, you can actually see this is actually the synchrotron light. So that glow you're seeing in there is in fact the photons being generated out the back end of the bending magnet that we're on this particular beamline. And because we're on a bending magnet, this is why we get a broader range of wavelengths. And then you put a crystal in and use a Bragg reflection to pull out just the wavelength you're interested in looking at. So that's actually what was going on in a real synchrotron. Let's say you get a source which is much more brilliant. The latest generation of synchrotrons are in fact the most brilliant known source of light in the entire universe. The only thing that we're going to have which is going to be brighter would be if some alien civilization has built a bigger synchrotron than we have.